Welcome back. Welcome to part 9 of our workshop. And as promised, we will tackle a full quarter of all of the Intel 8080 instructions, all of these move instructions. We'll do halt as well because it's pretty straightforward. It's pretty much as straightforward as NOP is. So we will have more than a quarter of all possible instructions assemblable with our assembler at the end of this episode. So let's start by actually implementing that move instruction, because we're going to see that as we implement that move instruction, we're going to have an interesting, let's say, new problem to tackle. So let's go ahead and say move. And move is, well, there's a lot of moves, aren't there? There's like 64 of them. I guess technically 63 because there's a halt in here. Okay, so how would we go about actually figuring out how to process move instructions? So something that sticks out to me is that every move instruction has 2 arguments. And those 2 arguments are always 2 registers. So on the Intel 8080, there's a number of different registers. There's A, B, C, D, E, H, L. And this is kind of pseudo register that they call M. So for our intents and purposes, let's say that there are 7, right? So there's A, B, C, D, E, H, L, and M are our 8 registers. So no matter what, if we see a move and we don't see registers, then something's definitely wrong. The next thing that looks interesting to me is that the registers appear to follow a pretty strict order. So if we look at the first register, we have all the B's, and then all the C's, and then all the D's, and then all the E's, and then all the H's, and then all the L's, then all the M's. We're going to ignore halt for now. And then all the A's. So the pattern is B, C, D, E, H, L, M, A. And each one of those, again, with the exception of M, we'll just ignore the halt, has 1, 2, 3, 4, 5, 6, 7, 8. The 9th one here begins with move C. So each register destination appears 8 times. So here the instruction is read move, B is your destination register. The first one is always your destination register. The second one is your source register. So for example, move D comma B says take the value of B and put it into D. So if you look at the ordering of the second argument, it follows the exact same pattern as the first argument. B always comes first, then C, D, E, H, L, M, and A. If we look over here, B, C, D, E, H, L, M, A, B, C, D, E, H, L, M, A, right, so on and so forth. So that appears to be the pattern of registers. And sure enough, if we look down below into our arithmetic operators, B, C, D, E, H, L, M, A, B, C, D, E, H, L, M, A, right? So that's clearly a pattern that seems to be constant throughout the entirety of the instruction set. And that is actually going to make our life significantly easier because there's a formula that we can apply to know which byte to output, because if you notice, every move is only 1 byte, but we can know based on the combination of having move as the instruction and the 2 arguments, which byte we should actually output. And the formula is going to be hex 40, and that makes sense because the very first move is at hex 40, plus, and then it's going to be the register times 8, or bit shifted by 3, plus the register. So we can apply this formula to figure out what the byte is going to be for each move instruction. So let's write out the move instruction first, and then we can go back and see what the actual formula is and write out the logic for that formula. So a move is going to be tokens, tokens, as always, output, output, as always. And then the logic is going to be check. And what is it that we want to check? We want to make sure that both arguments have values in them. So we want to make sure that the first argument is not empty and the second argument is not empty. Right? And then what action do we want to take? So the action that we want to take, all moves are 1 byte. So we can put 1 here for our third argument. And then we're going to need this formula here to actually output the correct byte. So we can just write it in right where we are. So hex 40 plus, I'm going to make a new function called register 8, and that'll be how we can figure out what number to give to each of these registers. So I'll say register 8 tokens.first times 8 plus register 8 tokens.second. And that's it. That is all we need to do to process a solid quarter of all of the instructions that we will possibly ever write. Very cool. But how about that register 8 function? So we need to figure out what the actual numeric value for each of these registers are. Let's take the second argument for the first set of moves, because that's going to kind of make it easier for us. So the very first move instruction is 40, hex 40, and that is move B comma B. Well, what's the only value of B that could make this formula make sense and yield hex 40? Well, that would have to be 0, because 40 plus 0 is going to equal hex 40. Anything else is going to equal something different. So it's probably going to be the case, if I had to guess, that B has the value of 0 when calculating register to instruction number. And indeed, B is 0. Move B comma C is 41. So what must be the arguments in this formula to get 41? Well, we already said B is 0. So hex 40 plus 0 plus what equals hex 41? And of course, the answer is 1. So C must equal 1. By the same logic, D must be 2, E must be 3, H must be 4, L must be 5, M must be 6, and A must be 7. And that is indeed the pattern that you will use anytime you see registers and need to convert them into an instruction number. So it's going to be exactly the same here when we get to our adds and subtracts. So let's go ahead and code that up. That's going to be fairly straightforward to code up. So we can say return the 8-bit register offset. So we want to return an int because we actually want to return the number. So we'll call this register 8, and it takes a string, and that string is the register that we've read in. And this is fairly straightforward. As we kind of saw before, D will allow us to do cases on strings. So let's go ahead and do that. So for case B, we want to return 0. Case C, we want to return 1. Case D, we want to return 2, and so on and so forth until we get to the end. H is next, and H is 4, and then L is after that. L is 5, M is after that, and it's 6, and finally we have A. And that's it. That's our whole logic for any time we see a register in some sort of argument for our instructions. So definitely for our moves and definitely for our arithmetic instructions as well. And that's it. We can now successfully process all of our NOPs and process all of our moves. But we should probably also, before we end for this episode, also process the halt. So one thing I'm not going to bother doing is if a user happens to put in, let's say, move M comma M, because the halt is in the location where move M comma M would be, I'm not going to worry about that. If a user wants to put that in, they can suffer the consequences, but we should definitely put in something for halt, because we may see halt as its own instruction. And this is going to be fairly straightforward. So at this point, we should know how to kind of set up the boilerplate for each of our functions. And so let's take a look at halt. Halt takes no arguments. So we want to check that, oops, let me just fix those there. We want to check that the first argument is empty and the second argument is empty. And then the action for us to take is 1 byte. Halt is only 1 byte, and it is hex 76. And with that, we can now process all of our moves, our halts, and our nops. So we're almost at the point that our assembler can be useful. We're not quite there yet, but we're getting there. So let's save this. And we'll say implemented move, halt, and register formula. Okay, and with that, we'll wrap up this episode, and I will see you in the next one.